Yeah, it's my pleasure to invite Lana Mineh from the University of Bristol to give us a discussion about strategies for solving the Fermi-Hubbard model on near-term quantum computers. I'm really excited to hear this talk today. It was a really interesting paper about this a few months ago came out, and I'd like to, really interested to hear more about it. Okay, thanks. Take it from here, Lana.
Okay. Yeah, thanks for having me. So I'm going to talk about how you would solve something like the Hubbard model on these NISQ devices. So this is like joint work with my supervisor Ashley Montanaro and also Chris Cade and Sazia Stanisha. So, right, I'm going to start with just a brief introduction to NISQ computing. Then I'm going to talk about the algorithm itself, the variational quantum eigensolver. Then I'll talk about the Hubbard model. And then actually after that, we'll talk about how I applied VQE to the Hubbard model and the numerical results we got. So NISQ stands for Noisy Intermediate Scale Quantum. So this is characterized by a number of things, a limited number of qubits. So the most qubits we have at the moment is on Google Sycamore, which is 53 qubits. So I would say NISQ is about in that range. There's a limited gate depth, so there's a limited number of gates you can apply before your qubits just decohere and become too noisy. There's limited qubit connectivity, so you can't just apply arbitrary 2-qubit gate between any 2 qubits. Everything's noisy, so there's noisy gates, there's readout error, and there's also no error correction, so you have to account for any errors yourself, either in the algorithm being robust to noise or just how you deal with noise afterwards. So the variational quantum eigensolver is one of these hybrid quantum classical algorithms, which is particularly suitable for the NISQ era. This is because basically you're using the quantum computer to speed up one bit, and you're trying to outsource as much of the work as possible to the classical computer. So the aim of this algorithm is to find the ground state of a given Hamiltonian. So the way it does this is we make a guess for the ground state in the form of an ANSATZ circuit. So I'll talk more about what these circuits look like later. We adjust parameters in this circuit by a classical optimization routine. And we just carry on until we've kind of reached a minimum value for the expectation. So this kind of works on the variational principle that states like the expectation of any state is bigger than the ground energy. So there's a couple of ingredients we need to specify for our algorithm. The first is if you have a qubit fermionic Hamiltonian, we need like a fermion to qubit encoding, and there's many we can choose: Jordan-Wigner, Bravik-Kitaev, Estrati-Chirac. The next thing is the ANSATZ itself. So you want to choose an ANSATZ that parameterizes a region of the Hilbert space that contains the ground state you're looking for. So this kind of step is really key because you need to pick the right family, the right depth, the right initial state, sometimes even like the right parameters. Next thing is how we actually implement the energy measurements. And finally, the classical optimizer. So this is a stochastic optimization problem because you won't get the exact expectation out of the quantum computer. So it's really important we pick an optimizer that's kind of robust to statistical noise. And finally, so this bit's kind of at the end. We need to do some kind of error detection techniques at the end. This isn't always necessary, but I'll discuss this later actually. Okay, so the Hubbard model. So this is one of the simplest models of interacting particles in a metal. So you have a lattice of sites, and on each site it can be occupied by an up electron and a down electron. And the interactions we have are this on-site interaction here, which is kind of like a Coulomb potential, and a tunneling term. So electrons can hop from one site to a neighboring site. So this model is interesting. Well, it's like widely studied in condensed matter physics, because even though it's simple, it kind of allows us to investigate how the interactions between electrons change the properties of a metal. So making it insulating, magnetic, superconducting, so on. The largest exact classical simulation was for 22 sites, and it required over 7 terabytes of memory on a 512 node supercomputer. So this is where we think quantum computers could be useful, because 22 sites would kind of map to 44 qubits, and you can kind of see that being within range in the next couple of years. Okay. Any questions so far? Okay, good. So how do we actually go about applying BQ to the Hubbard model? So the first ingredient was the fermion to qubit mapping. So we use the Jordan-Wigner transformation. So these transformations all preserve like the fermionic anti-commutation relations. The Jordan-Wigner, it basically keeps track of which sites are occupied by which electrons. So each site is represented by 2 qubits, because you can have 2 different fermions on that site. So one of the qubits keeps track of the up electrons, and the other qubit keeps track of the down electrons. So the state is 0 if it's unoccupied and 1 if it's occupied by a fermion. We actually looked at a bunch of other encodings in our paper, but we found that actually Jordan-Wigner was most efficient in our case for small grid sizes. So that was where the minimum of the grid lengths was less than or equal to 8, which is definitely within our range. So this is the actual Jordan-Wigner transformation, these 2 equations here. So the on-site terms become the projector onto the 1-1 state. And hopping terms are a bit more complicated. You get this like XX plus YY interaction between the qubits of interest here. But you also get like a Z string between qubits J and K. This is kind of like a parity correction. So yeah, all these equations map the fermionic grid to a line. So we need to pick an ordering for the fermions. So the ordering we use is a snake ordering. I'll show this in the next slide. And we order all of the down electrons after the up electrons. So this one here shows the ordering. So you can see it's kind of like a snake, which is why we call it snake ordering. This is actually a standard ordering when using the Jordan-Wigner transformation. And for both spins, this is what it could look like on something like the Google Sycamore architecture. So we've like labeled, say, all the ups are blue and then all the downs are red. Okay. So the next ingredient was the ANSATZ circuit. So like I said before, a good ANSATZ circuit will parameterize a region of the full Hilbert space that contains the ground state. So often ANSATZ circuits consist of a set circuit structure that repeats itself several times. And this repetition is referred to as the ANSATZ depth. This is different from the circuit depth. So an example of like a standard generic ANSATZ is something called the hardware efficient ANSATZ. You basically do a bunch of arbitrary single qubit gates, follow it by entangling gate, then you do like a more single qubit gates followed by entangling and so on. So this is probably one of like the most basic things you could come up with. It doesn't really use any properties of Hamiltonian itself. It's just like something generic that can be used for any Hamiltonian. So we can do a bit better by kind of tailoring our ANSATZ to the problem. So one of the ANSATZ we looked at was the Hamiltonian Variational ANSATZ. So this so this is based on intuition from the quantum adiabatic theorem. So the theorem states that one can evolve from a ground state of a Hamiltonian HA to a ground state of HB by applying a sequence of evolutions of the form e to the minus I t ha e to the minus I t hb, so sufficiently small t. So for the Hamiltonian variational ansatz, the ansatz that we start in the ground state of is the non-interacting Hubbard model. So if I just go back, if you look up here, the non-interacting thing is basically setting ut equals 0. So you only have hopping terms. So there's no interactions between the spin. So this kind of makes the Hamiltonian a quadratic one. So you can prepare its ground state efficiently on the quantum computer. Then another change from this adiabatic theorem is that instead of applying evolutions, you know, for the whole Hamiltonian, we alternate evolutions according to commuting terms in the Hamiltonian. So in the Hamiltonian, there's like, you can split it up into 5 commuting terms. So you can split it into the on-site terms, so that's everything attached to the U. And then 2 sets of horizontal and 2 sets of vertical. So if I go back to this graph, so basically the different colors represent the different commuting sets. So purple and orange are your 2 sets of horizontal terms, and blue and green are your 2 sets of vertical terms. So basically we kind of evolve in in some order. So you do on-site, then you might do horizontal, then you might do vertical, and then the other horizontal and vertical. Another crucial difference here is that these thetas don't need to be small, unlike these t's up here. They're just arbitrary angles between 0 and 2 pi that we kind of optimize using our classical optimizer. So I guess the thought is that, like, you're not tracing an adiabatic path to the ground state of the Hamiltonian you're looking for, but you're going kind of via another route. So the number of parameters you end up with here is 5 times the depth of the ansatz we choose. And the idea with this ansatz depth is that the higher the depth, the more likely you've kind of parameterized the region, parameterized the ground state you're looking for. In our paper, we actually generalized the Hamiltonian variational ansatz, and we came up with something called the number preserving ansatz. So we replaced all the hopping and on-site terms with a more general number preserving parameter, so this UNP here. So this operator comes from combining like the on-site and the hopping gates. So for one layer of the ansatz, we now apply UNP across each pair of qubits that correspond to fermions that interact. So before we were kind of evolving according to these terms, now we just apply like arbitrary number preserving unitaries everywhere that we have a connection. The nice thing with this ansatz is you can actually start in a computational basis state, because it's a bit more general than the last one, but you can also obviously start in the U equals 0 ground state as well. The number of parameters is now way bigger than before. If you remember, it was 5 times d. But it's kind of like a trade-off. So you might need a lower like depth of number preserving compared to Hamiltonian variational to reach the ground state. But this does make your problem a bit more complicated because you have a lot more parameters to optimize. Okay. So I'm just going to talk a bit about efficient ways of implementing these 2 ansätze. So all the on-site terms. Okay, so before, if you remember, we had on-site and 2 sets of horizontal and vertical. You can implement all the on-site terms in depth 1. What gets a bit more complicated is the horizontal and vertical hopping terms. So actually the horizontal terms can be implemented in depth 2. So if you recall that this is what the hopping terms look like, the horizontal hopping terms don't have this extra Z string. So horizontal hopping terms are basically just 2-qubit gates. So you can just apply your 2-qubit gates between, like within the commuting sets, and it's fine. So you can do all the purple ones first, then you do all the orange ones. What gets a bit more complicated is the vertical hopping terms. So basically, for example, if we wanted to implement this one here between 0 and 7, it's not just a 2-qubit gate, it's now an 8-qubit gate, because you need to apply your XX plus YY interaction here, and then you need to apply a Z string along here. So these can be quite costly to implement, as you can imagine, decomposing it down. So decomposing an 8-qubit gate to a bunch of 2-qubit gates. So to reduce this overhead, we implement something called a swap network. So yeah, we use F-swaps, so fermionic swap gates, to move qubits into positions where they're Jordan-Wigner adjacent. So what this means is that, so if you look at this, this one, this is the snake ordering. What we want to do is we want to move our pairs of qubits to the ends. So this is where they can interact. So if you remember the ordering, it was 0, 1, 2, 3, 4. These things are Jordan-Wigner adjacent because their numberings are right next to each other. So the way we do this is applying these gates, these ULs and URs. Yes, so if we apply UL once, so we would swap these 2 columns, and then we swap these 2 columns for, oh, sorry, yeah, for UL, and then we'd swap these 2 columns. Basically, these qubits here will end up at the end, and they get implemented first. So what this picture just shows is like, yeah, so which terms are implemented after, say, n times of applying UL. Any questions? Okay. Okay. So this is what our full circuit looks like. So the squiggly green lines are our number preserving or our Hamiltonian variational gates. So these are all parameterized, and these arrows are F swaps. So we start with our 2 sets of horizontal terms like before, and then to implement the vertical terms, we do this UL. So we do this swap network. The C and D need to be repeated, I think, 3 more times to have implemented every vertical term. A further improvement you can actually do is like folding in these horizontal hopping terms into the network. So you can see like these A and C, like we're applying kind of gates in the same on the same 2 qubits. So it turns out if you combine these 2, it's basically I think it looks like one of these gates, but up to like a single qubit unitary. Yeah, okay. Any questions? So this kind of this table just shows circuit depths of the efficient ansätze. So we tried, we kind of calculated these depths for 3 different architectures, so fully connected, nearest neighbor, and Google Sycamore. And you can see what the numbers look like for a 5x5 grid. So this is just kind of beyond the realm of exact diagonalisation, so solving it exactly classically. So a 5x5 grid would require 50 qubits. So if we look at Google Sycamore, the depth, so this is the circuit depth for 1 layer of the ANSATZ, would be 32. This is already kind of bigger than I think what Google Sycamore can do. I think it's about 20. So we're not quite there yet, being able to solve like the bigger instances. Okay, the third ingredient was the measurement. So at the end of each run of the circuit, we need to measure the energy. So again, we can actually split this into our 5 commuting sets as before. So we can measure all of the on-site terms in parallel, and then we can measure the 2 horizontal and 2 vertical in parallel as well. So if you recall, the on-site terms look like this, like projector onto 1, 1. These on-site terms can be measured simply by carrying out a computational basis measurement. So the energy corresponding to a particular site is the probability that the qubits corresponding to the up and down electron on that site are both measured to be 1. So this is good news for us. It's quite simple. The horizontal and the vertical hopping terms are a bit more complicated. So again, if you remember, the hopping terms look like this. If we first look at the horizontal terms, so that's not including these Z terms here, you can actually measure these XX plus YY things efficiently by transforming into a basis in which the operator is diagonal. And the operator that does this is this, so it's a C0 followed by a controlled hand mod followed by another C0. And you end up with this. So the expectation then is the probability of getting the outcome 0, 1 minus the probability of getting 1, 0. Vertical hopping terms are a bit more complicated because if you remember, it was like you have to consider so before it was like an 8-qubit gate, but here you also have to consider like the values on these qubits, like yeah, I guess because it's an expectation according respect to like 8 qubits, for example. But actually, it turns out that they can also be measured in parallel and at most 2 circuit preparations. So this operator U has the property that it preserves Z tensor Z. So we can apply U to all of these places here, all of these vertical terms here. And what this means is that you can kind of collect statistics for this XX plus YY thing. And you can also collect statistics for measuring Z tensor Z. So yeah, by applying U just to these things here, you can get this expectation, get that one, and get that one, and that one. Any questions? Okay. Right, okay. So the final ingredient was the classical optimizer. So the VQE algorithm makes many calls to the quantum computer. So some useful terms. So 1 circuit evaluation is 1 run of the quantum computer. To get 1 measurement of the energy, we need to do 5 circuit evaluations. And then to get 1 estimate of the energy, we then need to do M energy measurements. So this M needs to be quite big if you want to get really accurate answers. So we kind of determined a rough budget for the reasonable number of calls. So making some assumptions, so that 100 nanoseconds for to apply 2-qubit gate, single qubit gates, and measurements are instantaneous, and like an overall circuit depth of 100. Basically, in about 14 hours, you can produce 10 to the 5 energy estimates to an accuracy of 10 to the minus 2, if we take M to be 10 to the 4. So this kind of gives us a kind of a bound to be aiming for when we run like our actual simulations. Another thing is that we need an optimizer that is robust to noise. Yeah, statistical, just otherwise. We kind of tested 2 optimizers, so I'll talk a bit more about this later. We use something called SPSA, which is kind of a form of stochastic gradient descent, and coordinate descent as well. So this is, yeah, I'll talk about this in a minute. Okay. Any questions before I move on to the numerical results? So we ran a bunch of simulations and we did them with 3 levels of realism. So the first level is we simulated the exact energy measurements. So we kind of cheated and looked at the wave function. This tests which ansatz are most effective. So if you have a circuit which doesn't work well even with exact measurements, it's not going to work well when you've also added noise. The next stage was to simulate the measurements as if they were performed on a quantum computer. This kind of just tests how well the optimizers handle statistical noise. And there are some optimizers which just won't work at all. So this is a very important step here. And finally, we simulated energy measurements and quantum computer noise. So we did this with the depolarising noise model. So this tests how well the optimizers cope with additional noise. And we also tested a very simple error detection procedure, which I'll talk about in a minute. So the exact measurements, so in an initial test you can do to see how powerful these ANSATZ circuits are, is to determine the depth you need to go to produce the ground state to 99% fidelity. So along here I've got depth to 99% fidelity, and here it's like grid height. So the different colors are like the grid sizes. So we did 1 by n, 2 by n, and 3 by n. The different line styles are the ANSATZ we tested. So we tested just normal Hamiltonian Variational, which was in the original paper. We tested out efficient Hamiltonian Variational, which is the one with swap networks, and we tested number preserving ANSATZ. Yeah, so just to draw your eyes to some interesting things. So the number preserving ANSATZ consistently performs better than the Hamiltonian Variational and efficient Hamiltonian Variational. So it requires less depth to get to 99% fidelity. But this is kind of at a cost that you can't really see in this graph. It takes longer to run because you have more parameters. Yes. Okay. If we focus on the efficient Hamiltonian Variational ANSATZ, so for the rest of the results I'm going to show you, we focused on that because it was definitely the fastest to run. So for the largest grid sizes considered, so the largest grid size we went up to was something with grids of 12 sites, and there's 3 different ones that we've done. You can see the infidelity, like how it decreases with the ANSATZ depth. So this is a good sign. It shows that as we're adding the depth, we aren't just, it isn't futile. It is like improving our results, which is what we'd hope to see with this ANSATZ. Okay. The next step is realistic measurements. So again, we're fixing the Hamiltonian Variational ANSATZ. These results are for a 3 by 3 grid. We wanted to test SPSA and this coordinate descent. Yes, so SPSA is kind of, yeah, so it's kind of like a form of stochastic gradient descent, but this coordinate descent, it's, you're basically optimizing one parameter at a time. So say if you're want to optimize the first parameter, you kind of fix all the other ones and you kind of vary that to find the minimum. Yeah, so to compare the two, we fixed the number of circuit evaluations we wanted to do. So for coordinate descent, at every step, we kind of need really accurate estimates of the energy. So at each step, we're doing 10,000 measurements. This is kind of why this line looks smoother than the other one, because for SPSA we actually do a 3-stage optimization routine. So we modified normal SPSA to do this. We do like a very coarse measurements. So we take 100 measurements for each. Yeah, so we do 100 measurements followed by coarse, where we do like 1,000 measurements to get the estimate, and then finally smooth, where we want to get really accurate value, and we do like 10,000 measurements for the estimate. Yeah, so you can actually see like SPSA performs really well even with poor quality energy estimates. And SPSA has been around in literature for a while. It's like supposed to be really robust to statistical noise, so I guess that's kind of what we'd expect to see. Yes. Okay. This table just shows a few more grid sizes. So again, you can see like, so LBFGS is the exact optimizer. So this is without noise here. SPSA consistently performs better than like coordinate descent in this case. Okay. The next thing we did was noisy VQE. Here we considered a simple depolarizing noise model on top of everything. So after each 2-qubit gate, each qubit experiences noise with probability of P. So this model does like Pauli X, Y, and Z occurring with equal probability. We examined a couple of different noise rates, 10 to the minus 3, 10 to the minus 4, 10 to the minus 6. So this graph here is for 10 to the minus 3 error rate, and we did a 2x3 grid. And again, we did SPSA and coordinate descent. I'll just quickly talk about the error detection procedure, then come back to this graph actually. So we also tested something, a really simple error detection procedure. So the Hamiltonian is number preserving, and actually every operation in the Hamiltonian Variational and the number preserving ANSATZ also preserve the number. They preserve the fermionic occupation number, which is also, I guess you could call it the Hamming weight. So basically, when we detect an error by the Hamming weight being incorrect, we kind of discard that run and we continue the procedure until we have the required number of valid energy measurements. So this plus ED is plus error detection. So with SPSA, it doesn't have like a massive massive effect, but with coordinate descent, we do actually see an improvement by including this error detection procedure, even though it's like really simple. Another thing I should say is that it doesn't seem like the noise affects the fidelity too much. So this is a 2x3 grid. So if we go back here, kind of these were the values we were getting, so like 0.02. It doesn't seem too far off. Yeah, a 10 to the minus 3 error rate isn't having a massive effect on the results. This won't necessarily hold for an actual quantum computer. Yeah, it's quite interesting to see. Okay. Any questions? Okay. Right, conclusions. So for the exact measurements, results for efficient Hamiltonian variational consistent with a grid with n sites needing order n layers. And in fact, in all cases, we found that at most 1.5 n layers were needed. So this is good. So if we want to test bigger sizes, we can kind of immediately go to a depth that we think will reproduce the ground state. Realistic measurements, SPSA and both coordinate descent were able to achieve relatively high fidelity with the ground state by making a number of measurements which would take a couple of hours on a real quantum computer. And for noisy VQE, with simulated depolarizing noise, error rates of up to 10 to the minus 3 did not have a significant effect on the fidelity of the solution. Yeah. So it seems plausible that an instance of the Hubbard model larger than the capacity of exact diagonalisation, so anything maybe above like 24 sites or something, could be solved by optimising over quantum circuits with depth 300 to 500. Some future work in this area So noise and error mitigation techniques need to be investigated in more detail. So in particular, we only looked at depolarising noise, but something that's quite a problem on quantum computers is like readout error. So incorporating this in would maybe give us a better idea of how it actually works on a quantum computer. Determining the optimal choice of classical optimizer remains an important challenge, especially as we get a bigger grid size and the number of parameters goes up. So I think there's been a lot of work in like seeing if machine learning based optimizers would perform any better than the more standard ones. What happens when we actually run it on an actual quantum computer? So actually very recently, there's been a paper from Phasecraft, so from Ashley and Stasia, on this, where we actually ran the Hamiltonian Variational ANSATZ for a 2x1 grid on Righetti's architecture. So yeah, if you're interested in how it actually work on a quantum computer, I would check this out. And finally, we could maybe look to solid state physics for inspiration for other ansätze. So take into account even more symmetries of the Hubbard model. So things like translation invariance, spin invariance, things like that. Yeah, so thanks for listening. Are there any questions?
Clap, 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 clap. It's a bit hard to do claps virtually over this, so I guess everyone's clapping at home right now. So does anyone have any further questions I'd like to ask? If so, unmute yourself and ask away. But in the meantime, I just wanted to go back a couple of slides. I just wanted to see, like, how far do you project you can go? Like, how big a systems can we get to under this current noise model?
This noise model here?
Yeah.
I think the biggest we tested was maybe 3x3. The problem is, like, as you run bigger and bigger grid sizes, it takes ages to run. So, for example, 3x4, even with exact measurements, takes like several days to run on a GPU. So we can't really test how well it. We can't really go as far as like testing the noise on the bigger grid sizes. I would say, like, having seen like results of from like Ashley and Stasia's paper, like I think we're definitely improving the noise model is quite important, because I don't think this accurately represents what the quantum computer is actually doing. Like I said, there's a lot more errors like readout error and a lot more complicated stuff we're not really kind of accounting for in this like simple depolarizing noise model.
Okay, thanks for that. Do we have any further questions?
Yeah, so you were talking about an error rate of 10 to the minus 3, that it basically had no effect on fidelity. That's the 2x3 grid?
Yes.
So that's 12 qubits?
Correct.
At what circuit depth per iteration?
So we did a circuit depth. It goes back to this we're testing fully connected architectures, so
yeah.
It would be this. So I think circuit depth of 5. So this is basically maybe a total circuit depth of 15. Yeah.
So 12 qubits over depth 15.
Yes. Yeah.
So at that error rate, I mean, you've got an error rate of 1 in 1,000 and you've got 12 qubits over 15 time steps. I mean, you wouldn't expect any errors to occur really at that error rate.
Right.
So is that why you're seeing that the fidelity is not affected? Because you're effectively doing clean runs all the time?
I mean, probably. Like with these even lower noise rates, we really don't see any difference.
Mm-hmm.
And it's hard, like I said, to test like bigger circuit sizes. So yeah,
but
this could just be.
When you actually run them, do you have a flag in there in your code that sort of says, okay, in this particular instance, we an error was actually applied, to distinguish, like, because if you're going to do an error analysis of it, I would imagine you'd want to see exactly how this thing behaves when you do get errors, because you already know how it behaves when you don't have any errors at all, right?
I don't think we logged like what errors had occurred. It was more just like after every gate, just applying this like this noise model.
Right.
Because yeah, sometimes you're right. You would apply the identity and there'd be no error.
Yeah.
Yeah. So that would be really interesting actually to see like logging what errors occur and how it kind of spreads out and things like that.
Yeah, it's just, I mean, from my point of view, it's just, you know, is it the fidelity is not being affected because the circuit is, you know, quite robust to errors, or is it not being affected because you're statistically just not getting any errors?
Yeah, maybe it's like all the errors occurring kind of within the like the scope of like these SPSA and quant-descent algorithms kind of catch the statistical errors. It's not like big enough. Yeah.
Thank you.
Thanks.
And your error model, it's just depolarising Pauli channels, isn't it? Applied stochastically, it's not coherent errors at all.
Yeah, exactly. It's just this, depolarising.
So in that case, you don't get small errors that would cause effects. You just get errors that are large some of the time.
Yeah, exactly. Yeah, like phase flips. Yeah. Yeah, which is, I guess, why this like error detection procedure can kind of catch like some of these errors, because they're just big and obvious maybe.
Okay. Do we have any further questions? If not, so let's all thank the speaker again, which is kind of weird again in the virtual world. So clap, 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 clap. Thanks so much, Lana, for taking your time this morning or this evening, depending on what part of the world you're in, to give us this really excellent presentation on some really interesting work. It's been, really great. So, okay. Thanks, everyone.